So we want to study an abstract concept called groups. It is coming under abstract algebra. Abstract algebra. So for the group theory, you can refer Joseph A. Galien. His book is Contemporary Abstract Algebra. Okay, so I just outlined what we are going to study in this module. So we will study the definition and some examples. Then we move to a particular example called Klein 4 group. Right? So we'll see what it is. Then third, we have a particular group we call addition modulo n. We'll do that, or we will clarify all the titles corresponding video lecture. And a fourth one is multiplication modulo p, where p is a prime number. Then fifth one, we have a special kind of groups, which is permutation groups. Sixth, we have properties of groups, general. Then we move to something called subgroups. Okay. Eighth one is a special kind of groups, which is called cyclic groups. Ninth one is cosets. It's a particular kind of subsets of the group, right? We call it cosets. Last topic is Lagrange's theorem. Okay, so there are 10 topics, and there will be at least 10 videos, right? Yeah. So okay, so let's see. Okay, so we'll start by why do we need a group, and what is a motivation. So I would give you a practical example later, but now we will define things mathematically in more formal way, and we will so what's our idea is, we want to observe a very interesting set, integers. Okay, so what we are going to do is, we observe some properties of integers. So what is integers? This is plus or minus 1, like plus or minus 2 to infinity. We don't know what is infinity is going on. Okay, so that is Z, and so we observe some properties of Z and try to define a set G with similar properties. Then we end up with the classical definition of group. Definition of a group. Okay, so this is idea. Okay, so now a group is kind of a structure rather than simply a set. So a set with some structure. So in Z we usually use addition operation. Okay, so this is addition operation, right? And we observe one thing, that for any AB you take from Z, then you can see that A plus B is going to be inside Z, right? So this operation plus is we call closed in Z. Okay, we will see some other types of operations where if you take two elements from a set, it need not be inside the same set, need not be, right? So this is particular property we observe, and we call it is closure property. Closure property. Okay, so first case. So we will take inspiration from these properties and try to define what you mean by a group. Right now, in the same sense, I try to view this addition operation as a function from Z cross Z to the bigger set. Maybe we can talk about the bigger set we have is now it is real numbers, right? So if you take two elements from here, if you take A, take B, then you know that the elements of Z cross Z is looks like AB. So here the map is just A plus B. That is the, because plus is the addition. So addition can be viewed as a function from Z cross Z to real numbers. And what we observe that the range of this function, the range, what do you mean by the range? The f of the domain of that. So range of the function plus is a subset of integers, right? So that is a particular observation we have. Okay, for instance, if you take the operation subtraction and you choose some other set, like suppose you choose a singleton set 1 cross 1. So this is going to real numbers only, we are taking addition. So only one element is there in the A cross B, only the pair 1 1, and if you subtract this you get 0. So this 0 is not belongs to the singleton set 1. So it is not necessary that if you choose two elements from a set and the output should be in that, it is not necessary. But in the case of integers we observe that. Okay, let's keep that observation. Second thing is, if you add 2 plus 3 plus 4, we will get 5 plus 4, which is equal to 9, right? Also if you do 2 plus 3 plus 4, that means you first add 3 plus 4, okay, and do that. So 3 plus 4 is 7, and do this operation, so that's also 9. So what you can observe is 2 plus 3 plus 4 is equal to 2 plus 3 plus 4. So we call this property. So it is true that not only for 2 3 4, for any a b c in integers you can prove that a plus b plus e equal to a plus b then c. So that means we call it is associative property of integers, property of z. So we observe that property also. First we observe the closure property of addition inside integers. Second, we observe the associativity of addition in integers. Third, what I observe is we have a unique member called 0, right? What is the importance? So if you add for any number, for instance, if you add 2 plus 0, you get 2, you are getting 2 back, and also if you make 0 plus 2 also, you are getting 2 back. So what you can observe is for any integers x, you can see this property. If you add 0 plus x equal to x and x plus 0 equal to x. So we call 0 is identity of z under addition, under the operation plus. So such a member exists, right? So we observe that property. So we can call it this existence of identity, right? Fourth one is, once your identity is established, you can see that if you take 3, is there any element where you add that gets you the identity? Question is b inside integers? So if you solve this, you will get b equal to minus 3. Fortunately, minus 3 is in z. So for 3, minus 3 is in z. So what I am going to claim is, for any integer x in z, we have minus x in z, such that x plus minus x equal to 0 equal to minus x plus x, right? So we have this property. So every element there is an inverse, that's what we call, right? So there is a, so we can see the existence of inverse for every member in Z, right? So these are the main 4 properties we observe in integers, and what we are going to do is, so we are in search of, so I should write that, so we are in search of a Z like set with a addition like operation, right? So this operation behaves well in Z, that's why we can see. Okay, so we call Z plus a group. Okay, so I just said an example first, and we should look at what is exactly meant by group. So we'll go for a definition. So definition, group. So a non-empty set G, okay, in notation we call it as non-empty. Okay, a non-empty set G together with a binary operation binary operation star. So we call it a star, it can be anything. In our example it was addition. G cross G to G is said to form a group if the following holds, right? So first thing, so you need to understand one thing, that what you mean by binary operation is, a binary operation takes elements from G cross G and the output lies in G, then only we call it as a binary operation. So when you say binary operation, the meaning is that operation is closed, right? You don't have to say, so an operation is closed, we call it as a binary operation, right? So that's why I written like that. Now it's a closed in the beginning itself. Now we are going to see what are the other properties we observed. We observed associativity, right? So associativity. Now we are generalizing, it's not only for integers. So how do you generalize? For every a, b, c inside G, what we have? A, b, c equal to a, b, c. That means if you do the operation bc first, then you do with a, which is equivalent to you do ab first, then you c. So here actually this is written as a star b star c equal to a star b c, right? The star is the operation is here, but for convenience, okay, so I should clear it. So onwards I will be writing only ab. So this operation is not usual multiplication in real numbers, right? So that's very important. It is not. So it is just a notation, a star b. What is the operation? That's it, a star b. So that is the thing, associativity. You should have associativity in that. We'll see examples, then you will understand more what is all this mean by this. Now next is, we have seen 0 in integers. So similarly we force existence of identity. So what do you mean by existence of identity? That means there exists E inside G, and what is the property? For every x in G, this must happen, that is xc equal to x equal to ex. Okay, if you operate E with left and right, that should be x. So if such element exists, then we have a chance. So we need such an existence of such an element. Third thing is, once identity is established, we must have existence of inverse. Why do we need all these things? Because it makes the set more well behaved with an operation. That's why. Okay, that's the root of this definitions. Now existence of inverse, that means for every x in G, you should have there exists a y, and there must be a y in G such that xy equal to the identity equal to yx. So sometimes people will call this y as x inverse. Okay, it's a notation. So if y is the inverse of x, then vice versa. So x is the inverse of y. So please mark the, because we need to prove whether they are unique or not. Anyway, I am telling, if x is the inverse of y, then y is the inverse of x, because the symmetry in the definition, because symmetry in the definition. Okay, so these are the four things. First of all, it should be a binary operation. second associativity, third existence of identity, and second existence of identity, and another one is inverse, right? Okay, so now how do you check a given group, or you cannot say group? How do you check G with an operation star is a group, okay? So this is a question, right? If you're given something, how do you know that this is a group? So we need to observe some facts, right? That means why this definition is interesting, because this stands out, right? That's why. Right. So why it is interesting? Because there are there are operations. Why binary operation is interesting? Because there are operations which are not binary. There are that operations that are not closed. Okay. So you can see not all operations binary, or you can say, or closed. So can you give me an example? Think of an example. So an example is simply you take natural numbers under subtraction. So if you take 1 and 2 from natural numbers and you do 1 minus 2, your answer is minus 1. Unfortunately, minus 1 is not inside n. So that means the subtraction operation. So the subtraction operation from natural number n cross n, the bigger one on, it is not a binary, operation. What is the reason? Because the range of this set, you may remember, it is not a subset of natural numbers, because you get minus 1 which is outside that. Okay. That's why binary operations are interesting. Now, second, you need to observe not all operations are associative. Not all operations are associative. Okay, so you define subtraction function from integers to real number. So you can see that you can replace this to z, because if you take two real numbers, I mean integers, then a minus b also an integer. So this is a binary operation. The problem is whether it is associative. So take some examples. So try to do 2 minus 3 minus 4. You can see that it is minus 1 minus 4, it is minus 5. And if you do 2 minus 3 minus 4, this will be 2 minus of minus 1, this will be 3. And immediately they are not equal. So you can see 2 minus 3 minus 4 is not equal to 2 minus 3 minus 4. So not associative. Okay, that's why associative operations are interesting, because there are things which are not. Now let's check identity. So the identity is you may not have identity in a particular set under some operations. For example, you take the set we call something A. So this is all elements, this is natural numbers, difference the element 1. Okay, so what it is from 2, 3, 4, 5, like that. And you define operation addition on this. So addition on A cross A to A. Is it in a binary operation? Yes, because any number you take, if you add it, surely it is, if you take any number a, b, it is, if you add this thing, so this belongs to A because you are only adding things, right? There is no way to there is no way that you will get 1. Okay, so this is a binary operation, but you don't have an identity. It is also associative. So it is also associative because the bigger set n is associative, but no identity, right? Because the identity in addition has it is 0. If you talk about addition, even okay, I am talking about the multiplication also will work here. It is also associative. So I could change this to multiplication. AB goes to A into B. So if A into B, it is A. So 1 is avoided, and it is not. So no identity here. Even if you change n with addition, here also there is no identity because 0 is not there. 0 is not belongs to it. So identity may not exist even if there is a binary operation, right? So that's why existence of identity is not that not very common, right? Now how do you find if at all if there is an identity, how do you find it? So in Z, how do you find it? Z is the operation. So you know that identity means what? For any x, right, or you should take x arbitrary. Arbitrary means x can be anything. Then you find a what you can say, here you are solving for E. So what do you want to get? You get x plus E equal to x. From this, because addition operation, you get E equal to 0 because you know that it is in integers. So this 0 is independent of x. That is very important because it does not depend on x. That means that particular fellow works for anybody. Also, one more thing is you have to solve this equation also. Still E is equal to 0, and this has to match. Then this is also independent of x. And if these two equations match and it is E is independent of x, then you have an identity. We will see an example where it will not come like that, right? Yeah. So that's an idea. So for example, I want you to think of an operation like this. Star is an operation from Z cross Z to Z. So the operation is simple. A star B is equal to AB square. Okay, so this is the operation. It is very clear that AB square, if you do two integers you take, it is AB square again belongs to Z. So it's a binary operation. Whether it is associative, that is may not be, but I want to find if there is an identity. Okay, so what I am going to do is I want to solve these equations, right? So I want to solve A star E equal to A. First I want to solve this. Okay, this is my first equation. Let me see what I get. So this implies, what is A star E? The second part is square, right? So A E square is equal to A, and I am in integers, and okay, surely I cannot solve it if A is 0. So I assume A not equal to 0. Then I can cancel. So E square will be 1. So this will be E is equal to plus or minus 1. So let's keep it. So surely it is independent of A because it is a constant. You are getting two constant. We will see that. Now secondly, I want to solve the other equation, E star A equal to A. So E star A will be the E A square equal to A. So in this case also I assume A not equal to 0. Then what I will get is right. Yeah. So what I will get is EA equal to 1. So that's what I get. So EA equal to 1. So then E is equal to 1 by A. So this is a problem. E depends depends on A. Also they are not equal. So finally it is not going to work. So it is not possible to exist an element like that, right? So no identity exists. Okay, right? Because it should work for every A, right? But that's not what we get. We are getting. Okay. So right. Now even if identity exists, is inverse exist? So identity exists. Okay, for example, you take whole numbers with addition. What is whole number? Whole number is nothing but 0, 1, 2, like that. So here there is identity because 0 is identity. But if you take 2, how do you solve to get a inverse? You have to get 2 plus b equal to 0. Then b is equal to minus 2. That is not in whole numbers. So inverse doesn't exist. So if identity, even if there is identity, inverse is not there. So this definition is completely interesting because there are other cases, right? And also what I want you to understand that the properties 1, 2 and 3 in the definition of group is not redundant. Not redundant means nothing implies anything. That means if 1 implies 2, then I could remove 2 because 1 already implies that, but that is not the case. It is not doing that. And if 2 implies 3, then I can remove 1 because 2 implies 1. Then why should I have 1? But that is not the case. So similarly, none of them implies anything. That's why this definition is so concrete and so interesting. Okay, so we will see some concrete examples of groups and how to prove a given tuple, a set with an operation is a group. Okay, thank you.